Project 3.3.2 CHUMP Program EEPROM. This stage of the CHUMP project marks a major step forward in creating a functional stored program computer. In this build, two EEPROMs, one program EEPROM and one display EEPROM, work together to both store and visually represent the CHUMP's machine language instructions. The system now has the capability to permanently hold its code and show in real time which instruction is being fetched and executed. At the core of this stage is the program EEPROM, an AT28C16 chip that contains the CHUMP's 8-bit machine code written in Chumpanese. Each address corresponds to one instruction in the program. The SN74LS161 program counter provides a 4-bit address to both EEPROMs. Simultaneously, with every pulse from the 555 base clock, the program counter increments, advancing through the instruction sequence and providing a new address for the EEPROMs to read. The program EEPROM outputs the 8-bit instruction stored to the active address. This represents the binary command currently being fetched by the processor. Meanwhile, that same address is sent in parallel to the display EEPROM, which acts as a translator. The display EEPROM doesn't output binary instruction data. Instead, it outputs the corresponding 7-segment code that lights up the dual display. One EEPROM output drives the left digit, and the other drives the right digit, together forming a 2-digit hexadecimal display of the current instruction. As the program counter advances, the display updates instantly, providing a precise visual trace of program execution. Both EEPROMs are programmed using custom Arduino-based burn-in circuits that use the 74HC595 shift register to control the address lines. The Arduino sent each address serially, latched it through the shift registers, and placed the corresponding data byte on the data pins before pulsing the right enable line. A verification routine confirmed that each byte had been correctly written. The program EEPROM was loaded with the CHUMP's 10-instruction Chumpanese program, encoded as hexadecimal values. Each address location corresponds directly to one machine instruction, ensuring that the program counter's output sequentially retrieve the intended operations during runtime. The display EEPROM was programmed with a lookup table containing 7-segment codes for each possible instruction value. Each address corresponds to one byte representing the pattern of illuminated segments required to show the correct hexadecimal digit. Because there are 2 digits on the display, one EEPROM drives the high nibble, the left digit, while the other drives the low nibble, the right digit. Both receive identical address inputs from the program counter, but each outputs its own 7-segment pattern, combining to form a complete hexadecimal display of the instruction currently being fetched. Once programmed, the 2 EEPROMs were installed on the CHUMP breadboard. The program counter's 4 output lines were connected to the address pins A0 to A3 of both EEPROMs, with higher address lines tied to the ground to define a fixed 16-instruction range. The program EEPROM's data outputs were verified first using an LED bar graph to ensure that the binary instructions matched the programmed values. Next, the display EEPROM was wired directly to the dual ROM LB602A K2 7-segment display through current limiting resistors. One power up, each clock pulse from the 555 timer advanced the program counter, prompting both EEPROMs to read the next address and output their respective data. The result was a smooth, synchronized visual sequence of hexadecimal instruction codes, each appearing clearly on the dual display. This concludes Project 3.3.2 CHUMP Program EEPROM.